Welcome to the Explainer. Okay, today we're peeling back the curtain on the digital world. We're going to uncover the invisible math that powers, well, basically everything we do online. Because everything you see, hear, or interact with on a screen is actually just a massive illusion crafted by data. Let's dive right in. So here's our roadmap for today. We'll start with the digital voice illusion. Dig into bits, bytes, and speeds. Learn how to speak in binary. Check out the hexadecimal shortcut. Figure out how to handle negative numbers, and finally, calculate some digital storage. All right, part 1, the digital voice illusion. Have you ever heard about this happening? You're chatting online, maybe listening to this cute voice on a gaming platform, and then, bam! You find out later that the girl you've been talking to is actually some stingy old dude using a voice changer. It's kind of funny, right? But honestly, it's the absolutely perfect example of our digital reality. Behind the scenes, that cute voice isn't magic. It's strictly manipulated data. And that brings us right to our core concept, data representation. This is simply the process of taking real-world info, like a human voice, a photograph, or a text message, and converting it into a binary system for devices to process. Just zeros and ones. Because at the end of the day, underneath every single high-def image or altered voice, there's just a massive mountain of binary code. Moving on to section 2. Let's talk about bits, bytes, and speeds. Now, here is something absolutely crucial. We've got to understand the fundamental difference between how we store data and how we transmit it. This is a super common tech misconception. Getting this straight is going to clear up so much confusion about why your hard drive capacity or your internet speed never quite matches what's printed on the box. Take a look at the storage values here. When you're saving files on a hard drive or a flash drive, we use a base 2 system. The absolute basic unit is a bit, literally just a 0 or a 1. 8 of those bits make a byte. Simple enough, right? Well, here's where it gets fascinating. A kilobyte is not exactly 1,000 bytes. Because we're mathematically working with powers of 2, a kilobyte is actually 2 to the power of 10. That's 1,024 bytes. So megabytes, gigabytes, terabytes, they are all using that 1,024 multiplier. But contrast that with our transmission speeds. When you're downloading a file or streaming that voice changer audio, we totally switch gears to a base 10 system. In this context, the prefix kilo strictly means 1,000, exactly 1,000 bits per second. So if your internet provider sells you megabits per second, they are using that crisp, clean 1,000 multiplier, not the 1,024 we just saw for storage. It's a real game changer when you realize that. Okay, section 3, speaking in binary. To really understand the machine's native tongue, we've got to think about physical switches. Because a computer only has switches that are either on or off, it only knows 2 states, 0 and 1. To figure out how many unique patterns we can actually create with these switches, we use a brilliant little mathematical rule. The number of possible patterns is always 2 to the power of the number of bits. So 1 bit, 2 to the power of 1, just 2 patterns. But bump that up to just 3 bits, 2 to the power of 3, and suddenly you've unlocked 8 unique patterns. So how exactly do we translate our everyday base 10 decimal numbers into computer base 2 binary? It's actually a highly logical, step-by-step physical process. First, you repeatedly divide the decimal number by 2. Second, write down the remainder. And since we're dividing by 2, that remainder is literally always going to be a 0 or a 1. Third, just keep continuing that division until your quotient hits 0. And finally, to get your binary string, you simply read those remainders from bottom to top. That's the whole process. Let's actually see that math in action here. Say we want to convert the decimal number 118. We divide 118 by 2, right? That gets us 59, with a remainder of 0. Then divide 59 by 2. That's 29, with a remainder of 1. We just keep doing this division all the way down the line. Now check out the arrow on the screen. By reading those remainders from the bottom up, we can see that our everyday number 118 perfectly translates into the binary code 1110110. Which brings us to section 4, the hexadecimal short pack. So here's the core problem with binary. The strings of ones and zeros get excessively long. They are a total nightmare for humans to read and write. So, computer scientists use a clever workaround called hexadecimal, which is a base 16 system. The rules are super simple. Each hex digit perfectly compresses 4 binary bits into just a single character.
And since our normal numbers run out after 9, we just represent the values 10 through 15 using the letters A through F. It's a seriously elegant way to compress data representation.
All right, Section 5, handling negative numbers.
Wrap your head around this fascinating logic puzzle. How on earth do we solve the problem of not having a plus or minus sign? Remember, computers only have on and off bits. Well, look at the scale on the left. If we assume an unsigned integer scale, meaning no negative numbers at all, the binary string 111 naturally just means 7. But look at the scale on the right. If we program the computer to expect a signed integer, meaning it has to account for negatives, that exact same string of bits, 111, suddenly represents a negative 1. The bits literally didn't change at all. Only the context did. Digital systems pull this off using an incredibly elegant trick called 2's complement. By remapping the binary codes like you see in this table, the computer can seamlessly add, subtract, and represent negative numbers, like -4 or -3, using the exact same basic hardware. It's an ingenious mapping solution that makes complex computing possible.
And finally, Section 6, calculating digital storage. Let's apply all this. Take a look at these practical calculation scenarios. Imagine trying to figure out how many hours of a sound file you can physically fit onto a 40-gigabyte drive, if you know that 1 minute of sound takes up roughly 500 kilobytes. Or what about the second scenario? Imagine you've got 70,000 contestants in a programming competition, and you need to assign every single one of them a unique binary identity code. How much literal storage size, in bytes, is required just to store one of those identity codes in the system?
To solve practical problems like these, you just follow a very specific logic sequence. First, identify the data type and format. Second, rigorously convert all your units to a common base. And remember, this is where you absolutely cannot mix up your 1024 storage multipliers with your 1000 transmission multipliers. And third, apply our 2 to the power of b pattern rules. For those 70,000 contestants, you'd calculate what power of 2 gives you at least 70,000 unique patterns to ensure everyone gets a distinct code, and then convert those bits straight into bytes. We have covered an immense amount of ground today, all the way from the grand illusion of the digital voice down to the raw zeros and ones and back out to the real world. So to end this explainer, I want to leave you with a provocative thought and a bit of a brain teaser. Look at this final question. Can you arrange these 3 values, binary 101010, decimal 44, and hexadecimal 2b in ascending order? To pull it off, you've got to translate seamlessly across all 3 of those languages you just learned. So, can you decode the illusion? Think about it and keep exploring the incredible math that builds our digital world. Thanks for hanging out, and I'll see you on the next explainer.